Hello, welcome to this video lesson on relations. In this lesson, we'll understand through examples how to identify if a given relation is a partial order or is an equivalence relation. We do this using four examples defined on the set A, which contains five elements 0, 1, 2, 3, and 4. Let's focus on them one by one. Before we go into solving the problems, and let's just give a quick recap of what is called as an equivalence relation. The relation R defined on a set A is said to be an equivalence relation if it meets all three of the conditions given below. It must be reflexive, symmetric, and also transitive. The relation is reflexive if the ordered pair A, comma A is present in the set R for every A belonging to the set. So every element should be related to itself, and that pair should be present in the given relation. And if it is symmetric, it should meet the condition that if the pair A, comma B belongs to R, then the pair B, comma A must also belong to R. So if one pair is present, its symmetric opposite must also belong to the same set. And we call the relation as transitive if the pair A, comma C belongs to R whenever both AB and AB and BC belong to R. If both AB and BC belong to R, then this should imply that the pair A, comma C also belongs to R. These three conditions are met, a given relation is said to be an equivalence relation. However, the relation is said to be a partial order if it meets the three conditions defined below. Two of them are already discussed. It must be reflexive, it must be transitive. The second condition is slightly different. This relation R will be called as a partial order if, in addition to being reflexive and transitive, it is also anti-symmetric in nature. The relation is anti-symmetric if for any two distinct elements A and B, at most one of AB or BA must belong to R. In other words, if A and B are different, we cannot have both AB and BA belonging to R. For different elements, both AB and BA cannot belong to R. We can have a maximum of only one, not both. If both are present, it is not anti-symmetric. We can have neither. So you need not have either AB or BA. Both of them can be absent, but both of them cannot be present. Such a relation is called as an anti-symmetric relation. And I would like to draw your attention to the fact that a relation being not symmetric and the relation being anti-symmetric are totally different notions. We'll understand them through the examples. The first example that we'll pick up is the relation R1, and R1 is of this kind. R1 has these ordered pairs. There's 10 ordered pairs, and it's quite obvious that R1 is not reflexive. R1 is not reflexive. Why do we say that? Because the pairs 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4, which must be present in the set, are absent. For every element belonging to the set A, we must have the reflective ordered pair as part of the relation. These must be present, they are not. We don't find any of these ordered pairs in R1, therefore this relation is not reflexive. Further, so we have already ruled out that it is not reflexive. Let's consider the transitive case. The transitive case again, we need to check the condition that the pair A, comma C must be present whenever the pairs AB and BC are present for all elements A and B belonging to the set. As an example, I've considered the pairs 1, 3 and 3, 2. If 1, 3 and 3, 2 are present, then 1, 2, the pair 1, 2 must also be present. This is obvious and it is observed also. 1, 3 is here, 3, 2 is here, 1, 2 is here. This qualifies as an example of an ordered pair which meets the transitive condition, but this must be observed for every A, B, and C belonging to the set. So I mean, checking for the transitive nature is a time consuming process. So we'll consider different choices of A, B, and C. When we pick 4, 3, and 3, 4, We must also find the pair 4, comma 4 belonging to the set, but that's not the case. We have 4, 3 over here. We have 3, 4 over here, but the ordered pair 4, comma 4 is absent, and therefore our relation is not transitive. So it has failed to meet two of the three conditions. It is not reflexive, it is not transitive. Let's explore further. We'll consider the symmetric case now. We know the definition behind the symmetric case. A relation is said to be symmetric if we observe that whenever the pair AB belongs to R, the pair BA must also belong to R. Whenever AB belongs to R, the pair BA must also belong to R. That's actually observed in this example. When 1 comma 2 is present, 2 comma 1 is also present. When 1 3 is present, 3 1 is also present. When 2 3 is present, 3 2 is also present. When 1 4 is present, 4 1 is also present. When 4 3 is present, 3 4 is also present. This is observed for every a comma b belonging to the set A that we considered here. Therefore, our relation R1 qualifies to be a symmetric relation. Let's explore the anti-symmetric nature. We saw before that for a relation to be anti-symmetric, there is a special condition to be followed, that if A and B are distinct, both pairs AB and BA cannot belong to the set. Here, however, though, we see that both 1 2 and 2 1 are belonging to the set R1. They are belonging to the set R1. Therefore, our relation R1 is not anti-symmetric. If it is anti-symmetric, only one of these two pairs is permitted, or you can have neither of them. But unfortunately, though, in this case, we have both pairs, 1, 2, and 2 1 as part of the relation. Therefore, R1 is not anti-symmetric. To sum up, we see that our relation R1 is not reflexive, is not transitive, and it is in fact symmetric. It meets only one of the three conditions necessary for an equivalence relation. Therefore, R1 is not an equivalence relation. R1 is not an equivalence relation. And let's also examine the case where R1 may be a partial order. Partial order again demands three conditions. It has to be reflexive, it has to be transitive, it has to be antisymmetric. We see that it meets none of the three conditions required for being called as a partial order. So this will mean that R1 is also not a partial order. R1 is not a partial order. So it is neither a equivalence relation nor a partial order. That's the outcome of the first example that we discussed. We move to the second example containing 7 ordered pairs collected from the set A 0, 1, 2, 3, 4. The first thing that we note once again is that it is not reflexive because the ordered pair A comma A must be met for all 5 elements of the set. Here we do have 1 1, 2 2, 3 3, and 4 4, but the pair 0 comma 0 is absent. This is not part of R2. This must belong to R2 for it to be called as a reflexive relation. It's not the case. So R2 is not reflexive. So we have ruled out one of the three conditions. Let's consider the symmetric nature. And once again, it's quite obvious that this relation is not symmetric. Why do we say that? We know that for it to be symmetric, if A comma B belongs to R, the pair B comma A must also belong to R. However, we do note that the situation is such that 1 comma 2 belongs to R but the pair 2, 1 does not belong to R. And even if it fails for one such pair, it totally ruins the possibility that it is a symmetric relation. So of course, we note that R2 is not symmetric. So it is not reflexive, it is not symmetric. Let's explore the other cases. However, though, we find that it is antisymmetric. Let's recall the definition for the antisymmetric nature. For any two distinct A and B, at most one pair AB or BA must belong to R. But both cannot belong to R. If both are belonging to R, then it is not antisymmetric. It doesn't meet the condition there. So we look at this situation here. We have 1, 2. We do not have 2, 1. That's noted. We have 2, 3. We do not have 3, 2. That's again noted. We have 1, 3. We do not have 3, 1. That is also noted. For every distinct A and B, we see that we do not have both pairs present. We do not have both pairs present. Therefore, R2 in fact qualifies to be an antisymmetric relation. Next, we move to the transitive case. Like I told you before, arguing in favor of the transitive nature will take time. So we'll discuss all possible ordered pairs here. We'll start with pairs which begin with 1. So let's compare 1, 1 and 1, 2. This should result in the pair 1, 2, and 1, 2 is present. 1, 1 and 1, 3 should result in 1, 3, which is also present. 1, 2 and 2, 3 should result in 1, 3, which is also present. Moving further, 1, 2 and 2, 2 should mean that 1, 2 is present. That's there. 1, 3 and 3, 3 should mean that 1, 3 is present, which is also noted. 2, 2 and 2, 3 should mean that 2, 3 is present. That's there. 2, 3 and 3, 3 should mean that 2, 3 is again present, which is also happening. So we have considered all possible ordered pairs for all choices of A, B, and C, and we see that they meet the conditions necessary for the relation being called as a transitive relation. So therefore, we conclude that R2 is transitive, as we just saw. R2 is antisymmetric. We saw a couple of slides back. However, R2 is not reflexive. R2 is not symmetric. So we conclude that R2 is not an equivalence relation because it meets only one of the three conditions, that it is transitive. But these two, the reflexive nature and the symmetric nature, are not met. Similarly, R2 is not, I meant to write a not here, R2 is not an equivalence relation since it meets only one of the three conditions. And R2 is not a partial order because it meets only two of the three conditions. It is transitive, yes. It is antisymmetric, yes. But it is not reflexive. So once again, it is not a partial order. So this relation also is neither an equivalence relation nor a partial order. Let's explore the next example. The next example contains 11 ordered pairs. All of them have been picked from the set A containing 5 elements 0, 1, 2, 3, and 4. The first thing that we note is that this relation R3 is in fact reflexive because for every A belonging to the set 1, 2, 3, 4, for every A belonging to the set 1, 2, 3, 4, we see that the pair A, comma A is present. We have 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4. Therefore, this qualifies as a reflexive relation. However, though, we see that it is not symmetric because we observe the case that there is a 1, 2, but there is no 2, 1. It fails for one pair, and that is enough for us to come to the conclusion that it is not symmetric. It is not symmetric because one of the pairs is absent. We have only 2, 1, we do not have 1, 2. So it is reflexive, but it is not symmetric. Let's look forward to the condition that if it meets the necessary requirements for it being an anti-symmetric relation. And we see that it is in fact an anti-symmetric relation because the pair 1, 2 is present, but its opposite 2, 1 is absent. We have 2, 3 present, 3, 2 is absent. We have 3, 4 present, but 4, 3 is absent. 1, 4 is present, 4, 1 is absent. 1, 3 is present, 3, 1 is absent. 2, 4 is present, 4, 2 is absent. So for any A and B, we have at most one of the two pairs present. They are not, both of them are not present. Therefore, this relation is in fact an anti-symmetric relation. Like I told you before, a relation not being symmetric doesn't mean that it is definitely anti-symmetric. For example, had I included, suppose we consider the case where 4 comma 2 is present in R3, then the last case would be wrong because I have both 2 4 I have both 2 4 and 4 2 as part of the set. I have both 2 4 and 4 2 as part of the set. Therefore, this will mean that for distinct choices of A and B, like 2 and 4, both pairs are present. Therefore, it is not anti-symmetric. So this will, if this pair is included, then R3 cannot be anti-symmetric. So just because it is not symmetric doesn't mean that it is by default anti-symmetric. The two conditions are different. That's why we use the word anti, and that has a significant meaning there. This is not the case. I'm erasing this. So in this case, though, we see that it is definitely anti-symmetric because 4-2 was in fact absent. Then let's consider the transitive nature, for which we'll consider different choices of A, B, and C. Let's pick 1, 2, and 2, 3. This should result in 1, 3, and 1, 3 is present. 1, 2, and 2, 4 should result in 1, 4, which is present. 1, 3, and 3, 4 should result in 1, 4, which is also present. 1, 2, and 2, 2 should result in 1, 2, which is present. 1, 3, and 3, 3 should result in 1, 3, which is present. 1, 4, and 4, 4 should result in 1, 4, which is also present. So all pairs beginning with 1 have been checked. When we go to pairs beginning with 2, 2, 3, and 3, 3 should result in 2, 3, which is obviously there because that's where we started. 2, 4, and 4, 4 should result in 2, 4, which is again present by default. 2, 3, and 3, 4 should result in 2, 4, which is in fact present. Let's go to pairs that begin with 3. There's only one pair that begins with 3. 3, 4, and 4, 4 should result in 3, 4, which means 3, 4 is also present. So we have considered all possible choices of A, B, and C, and therefore we conclude that R3 is in fact transitive in nature. So to sum up, we see that our relation R3 is reflexive, is antisymmetric, and is also transitive. So the first conclusion we make is that this is not an equivalence relation because an equivalence relation will demand that it is also symmetric. It is not an equivalence relation. However, though, we see that R3 is a partial order. The partial order only demands that it is reflexive, transitive, and antisymmetric. In our case, though, we see that it is in fact meeting all the three conditions necessary for it to be called as a partial order. Therefore, R3 is a partial order. We'll explore the fourth example next. Fourth example is once again constructed from the set A containing 5 elements. So 5, 7, 9, and 11. There are 11 elements in the set R4. And first up, we observe that it is in fact reflexive because we do see that the property, the condition is met. 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4 are part of the set. Therefore, it is in fact reflexive. That's pretty obvious. Okay. Next up, we see that it is also symmetric. The reflexive nature has been checked. It is reflexive. Let's explore the symmetric nature. Of the two pairs 1, 2, and 2, 1, we see that both are present. So if 1, 2 is present, it should mean that the pair 2, 1 is also present. That is the case, of course. We see that 1, 2, and 2, 1 are present. Similarly, 2, 3, and 3, 2 are present. So the presence of 2, 3 has resulted in the presence of 3, 2. and the presence of 1, 3 has resulted in the presence of 3, 1. So all the symmetric pairs of elements are also present. Therefore, it is in fact symmetric in nature. Go to the next one. Of course, it is not anti-symmetric because for the choice of 1 and 2, we see that both 1, 2 and 2, 1 are in R4. We have 1, 2. We also have 2, 1. Therefore, it is not anti-symmetric. That's pretty obvious. The last part, we'll explore the transitive nature by considering pairs that begin with 1. So 1, 2 and 2, 3 should result in 1, 3, which is present. 1, 2 and 2, 1 should result in 1, 1, which is present. 1, 3 and 3, 2 should result in 1, 2, which is also present. 1, 2 and 2, 2 should result in 1, 2, which is present. And 1, 3 and 3, 1 should result in 1, 1, which is present. 1, 3 and 3, 3 should result in 1, 3, which is present. Consider 2, 1 and 1, 1 should result in 2, 1. Obviously, it's the last pair. 2, 1 and 1, 2 should result in 2, 2, this here. 2, 3 and 3, 2 should result in 2, 2, this again present. Likewise, 2, 1 and 1, 3 should result in 2, 3. 2, 3 and 3, 1 should result in 2, 1. And 2, 3 and 3, 3 should result in 2, 3. That's present again. And there are two more pairs that begin with 3. 3, 1 and 1, 1 should result in 3, 1. Yes. 3, 1 and 1, 3 should result in 3, 3. Yes. 3, 2 and 2, 2 should result in 3, 2. That is also present. Exploring three more choices, 3, 1 and 1, 2 with 3, 2. 3, 2 and 2, 1 with 3, 1. 3, 2 and 2, 3 with 3, 3. All of these are met, and therefore we conclude that our relation R4 is reflexive, is symmetric, and is also transitive, and therefore we can call R4 as an equivalence relation. This meets all the three conditions necessary for it to be called as an equivalence relation. However, we can also note down that it is not a partial order. R4 is not a partial order since it is not antisymmetric. Since it is not antisymmetric. So it is not a partial order, it is only an equivalence relation. That brings us to the end of the problem that we began to discuss. We see that our relations have met, some of them have met all the conditions necessary for an equivalence relation, some of them have not, some of them have met the conditions for a partial order. The next video lesson, we will discuss a problem which focuses specifically on a partially ordered set, and we'll try and define its Hasse diagram, its digraph, and we'll also find if it has greatest elements, least elements, lower bounds, and upper bounds. We'll take that up in the next session. Thank you.